TOF, off delay timer, or timer off delay. The original intent of this instruction was to delay the off state of a bit in memory for the length of the timer's preset, delay off, after the condition went false or an event ended. So with an off delay relay timer, the old-fashioned kind that you plug into a socket, has a little dial on top to dial in the delay, you energize the relay and the contact closes, the normally open contact closes, and then when you de-energize the relay, meaning that you remove the signal from the relay for it to be on, the timer started timing and it held the contacts closed until the timer had timed out. Therefore, it delayed the off state, so to speak, of the relay contacts. So the TOF instruction, that's what it's up to. I never use this instruction in the field because of its confusing description. We will show you later how to use a TON to accomplish the same off delay that you would get with an off delay timer. But we're going to cover the timer because it is part of the instruction set. We're going to make this really easy for you because some of us only have the 1769 IQ6XOW4, 6 inputs, 4 outputs. We will reuse our existing logic. So open your existing project, which you see in front of you, and save your project as beginner L, whatever your processor number is, TOF plus input. I'm going to do that. And you see that it's simply a matter of changing the N to an F on the existing file and saving it. All inputs off. Offline or online, your choice for the next edits. I'm online, so I'm going to keep it online. Now remember that I have my display here all kind of skewed around. I have things stretched. I have things up a little higher. I've moved the toolbars around to allow more space for my logic, so we can see the logic and we can see the bits in the watch panel. So you see what I did, and I could go one more further and move these down here and get even more height, but this is enough for right now. So what I had you do was put this in the edit mode. If you're offline, you don't have to put it in the edit mode, you just start editing. Double click on the instruction. I can drill down and select a TOF, or I more simply just backspace, type in F, enter. That data type, that my time data type timer, scope, main program, that's not an undefined tag. What you just witnessed, because I changed it, that instruction, to a TOF while online, even though the tag was defined, I had to type in the preset and the accumulate before it would accept it. If you did it offline, you ran into less trouble. So let's finalize all edits. Remember, my toolbars are all moved around, so I have to come over here to finalize all edits. Drag this back up, go to the watch panel, so I can see all my logic and I can see the data table in the watch panel down here. In the online run mode with your new logic, make a note of the state of the bits that are now controlling outputs on your output module. Once duly noted, toggle input 0 on again and watch the bits. I've already triggered this thing because I turned it on. Notice that it's not timing. The enable bit is on and the done bit is on. So if you're thinking, wait a minute, how can it be done if it hasn't timed out? Well, that's exactly how it works, and that's why I don't care for this instruction, but don't let me bias you. We're going to go ahead and examine this instruction. What I don't like is that the done bit comes on before the timer is timed out. But it's the way the timer data type works, and that's what we have. In what order did the outputs come on? Watch and think carefully. Leave blank if no change in state. So I'm going to turn this off, let it time out, so we can get back to the beginning so you can watch it again. Now we don't need 10 seconds. I'm going to reduce this down to 5,000 milliseconds, thousandths of a second. And right now, with the rung false, all the bits are off. It's not enabled, it's not timing, and it's not done. When I flip it on, the enable and the done bit come on at the same time. The question in the book, in what order did the bits come on? Well, the enable and the done bit came on simultaneously. We'll write a 1 next to done and enable. Now, let's turn the switch off in the timer timing bit. Now let's see what order they went off in. Well, that was too fast for me. So I'm going to do that again. 5 seconds might be longer than we need to wait. I'm watching very closely. Well, it's hard to say. What order did the outputs go off? Well, the enable went off right away. See? So the enable bit was first, and I would say that the done bit and the timer timing bit were simultaneous. You could logically say that the timer timing went off first, then the done bit, because when it was done timing, then it was done. I couldn't prove it either way, but either of those answers are good. The first group would have been 112 and the second group 212. The important thing is that you understand the behavior of the bits. Okay, disable the TOF instruction, which it is. Look over the chart below and then enable the TOF instruction. Observe and fill in the order of the events below, putting a 1 in front of the first in sequence, a 2 next to the second thing that happens, and so on. After you have recorded the initial state changes, then disable the instruction by turning off input 0 to complete the sequence of transitions. If you think that more than one change state at the same time, simultaneously, put the same number for all of these. If I flip this on, I see the enable and the done bit going on. So if I look at my list here, you'll want to pause to fill out this chart. You may have to do it a bunch of times. This is a really very difficult application here. The TOF instruction seems illogical, but it does function correctly. So you'll have to take your time putting in the sequence of events. And it really depends on where you start, with the input on or the input off. The manual said disable the TOF, look over the chart below, then enable the TOF, observe and fill in the order. So if you start with the TOF disabled, then turning it on would be step 1. It depends on whether you are going from a disabled and then starting, or going from an enabled and then turning it off. So first let's start with it disabled in the state that you see right in front of you. So if I turn it on, turn that input on, the first thing is input 0 is set to 1. Number 2, the rung goes true, obviously. And then number 3 is the accumulate clears and the enable bit is set on. And the done bit is set on, and that's the way you see it right now. And it sets like that until you turn it off. At this point, the next step would be to turn it off. Number 4 then, following 3, in other words, you had 3 of them at number 3. Input 0 is set to 0, 4. 5, the rung goes false. And then 6, the enable bit is set to off. When the enable bit is set to off, it starts to accumulate, the accum increments, and the timer timing bit is set to 1. When the accumulate equals the preset, right below that, that would be 8. And after the accumulate equals the preset, then the done bit goes off and the timer timing bit goes off, that would be 9. And that's what you see right there. If you want to do this starting with it off, then turn it on to start the sequence. Then the first column would be 3, 7, 2, 7, 8, 9, 4. The second column would be 5, 6, 9, 3, 3, 1. Now if we do it just the opposite, we turn it on and start this way, then again you need to take some time and execute it. Notice that I bumped it up to 50 seconds. So I had plenty of time to watch what it was doing. I'm going to knock it back down to 5 seconds by taking a 0 off of that. With that longer time, it allowed me to really look at it and think about it, because I even struggle a little bit because I don't use this instruction. I'm not intimate with it, but I do understand it completely. You will see that as we keep going. If we start with it on and then turn it off, then number 1 is going to be, we're starting with it on now, like it is right now. So the first thing we do is we set it off. The second thing that happens is the rung goes false. The third thing is that my timer timing bit is set to 1. The enable bit is turned off. Then number 4, it accumulates. Number 5, the accumulate equals the preset. Number 6, the timer timing bit is set to 0. The done bit goes off. Number 7, we turn the input back on. Number 8, the rung goes true. Number 9, the done bit is set on. The accumulate clears and the enable bit is set on. If you look at the 2 columns, the first column would be 9, 4, 8, 3, 5, 6, 1. The second column would be 2, 3, 6, 9, 9, 7. Save your project. I'm going to save it, and you see that's pretty quick because we have Ethernet. The next several pages in the manual will compare the TON and the TOF instructions. If you cannot follow the comparison, you might want to go back to the project for the TON and review it, followed by reviewing the above TOF logic, and then proceed again from here. In the manual, we did side-by-side comparison between the 2 instructions. We took the logic that we had in the previous lab, where we had input 0 enabling a TON, and then we had the enable timer timing and done bits controlling output 0, 1, and 2. And then side by side we showed it with the TOF instruction, with input in the off state, with input 0 in the off state. In other words, both of the instructions disabled. All bits are in the identical state. They look equal. But this is where the similarity ends. Switch input 0 to the on state, enabling both timer instructions. Are both timer instructions incrementing units of time? Now, in order for you to do this, you would have to go back and open up that other project, look at it for a while, and then come back, close it, and open up this one and look at it for a while. You can't have them both running at the same time. I mean, you could have created 4 more rungs and used different tag names and maybe done it that way. Are both timer instructions incrementing units of time? Now, you can also look at your chart where you filled in the sequence of steps and answer that. No, they're not. The TON is incrementing as soon as it's enabled. The TOF does not increment until the rung goes false, from true to false, because it's an off delay, not an on delay. When did the done bit set in the logic on the right side, on the right set of rungs? That would be, when did the done bit come on for the TOF instruction? It comes on as soon as it's enabled. Which 2 bits are in the opposite state? Well, they would be timer timing and done. With the TON is timing, the done bit is not on. When the done bit goes on, the timer timing bit goes off with the TON. With the TOF, the done bit comes on right away. Then when it's timing, the done bit stays on until the timer timing bit goes off, then the done bit goes off. So which 2 bits are in the opposite state? I would probably answer that question that the timer timing and the done bit, because they're both enabled. If I enable this, see, the enable is on. So whether it's a TON or a TOF, when you flip the input on and you enable it, that behaves the same, so to speak. It's the done bit and the timer timing bit that don't behave the same. After an interval of time exceeding the preset value, are both my time done bits in the on state? No, they're not. When the TON is accumulating, is the TOF accumulating? No, it is not. Which instruction has its timer timing bit in the on state? That would be the TON, the one that is accumulating. The answer would be yes, the one that is accumulating, or the one that is not accumulating, no. So the timer timing bit is always on when it's accumulating. Which instruction has its timer timing bit in the on state? The answer would be the one that is accumulating, yes, or the one that is not accumulating, no. Did both instructions begin accumulating the instant that we enable the timer instruction? No. Which did begin accumulating when we enabled the instruction? The TON. Which did not begin accumulating when it was enabled? The TOF. And we had some more side-by-side comparisons, and we said, are both done bits on? Yes, they are. The difference is, when you look at those two side-by-side, the one on the left is the TON. It's done because the accumulate has now hit the preset. The one on the right, the TOF, it's done as soon as you enable it, and it stays done until you disable the rung, lets it time out, and then the done bit goes off. Switch input 0 to the off state, disabling both timer instructions. Did they both reset to 0? No. What is the TN doing after input 0 is switched to off? Nothing. It's cleared. What is the TOF doing after input 0 is switched to off? Well, the timing bit is on and it's accumulating. Once it gets done accumulating, the timer bit goes off and the done bit goes off. All the bits are off. After exceeding the preset, do they both look identical again? Yes, they do, as you can see in the last comparison on that page. Did the done bit change to 1 when the TON instruction had finished accumulating? Yes. Did the done bit change its state to 1 when the TOF had finished accumulating? No. That's the single biggest difference right there. This is the reason that most folks avoid the TOF instruction, because when it's done, it hasn't started yet. And then it stays done until it really is done, and then it's not done. Now read that. It's in your manual. Read this over and over again until it makes sense if you have the TOF control bits in mind. Let's look at that again. At the top of the page, there are two questions. They're identical, but one is asking about the TON and the other the TOF. When the done bit changed its state to 1, when the TON instruction had finished accumulating, did the done bit change its state to 1 when the TON instruction had finished accumulating? Yes. Did the done bit change its state to 1 when the TOF instruction had finished accumulating? No. And the reason, again, that this instruction is confusing, if you look at the done bits, the timer timing bit makes sense. It's the done bit that is the fly in the ointment. Because when it is done, or when it's done, meaning the done bit is on, it hasn't started yet. So if you look at it right there and I turn it on, okay, the done bit is on. You're looking at it. Nothing's happening though, right? And it'll sit just like that until you get bored and change something. I'm going to just sit there for hours and hours, days and days. Nothing's going on. But it says it's done, right? The done bit is on. Done, it hasn't started yet. And then it stays done until it really is done, and then it's not done. So I'm going to flip this off. The done bit's still on. It stays done until it's done. It's timed out now. The cum equals the preset. So in a sense it's done, but now it's not done. The done bit's not on. So I think you follow that and you see why it's confusing and why you might want to avoid the TOF instruction. Remember that you can edit the instruction type back and forth between TON and TOF to compare the TON to the set of illustrations on the left side of the comparison and TOF to those on the right side. Now, if you're not going to worry about the TOF instruction, then I would move on. Since we can see that the enable bit is on anytime the rung condition is true, we can eliminate the rung that controls an output with the enable bit. We do this to keep the number of outputs used to 4 in this next sequence. Basically, going to go to this rung right here, select it, hit delete, go down here, finalize all edits, and it's done. We've shortened up our watch panel a little bit, and we've also shortened up our logic. So we don't really care about the enable bit because if the rung's true, the enable bit's going to be on. Timing events. All use of timing devices, whether a stopwatch or the predefined data type timer, all use of timing devices is predicated on an event. There is no measure of time before the event starts, only from when it started or from when it ended. In conventional terms, we refer to this as the leading and trailing edge of the event interval. We had a diagram in the manual that showed a pulse that represented the event interval. The TON instruction dominates the interval and can be extended beyond the trailing edge of the interval by use of the done bit as a true if off instruction to seal in the TON instruction. Once the TON is timed out, you can use the done bit to keep the TON enabled. The TOF instruction dominates the timeline from the trailing edge to the limits of the instruction's preset value. You see in the diagram we have TON primary, TON extended. The TON primary, that's the event interval. But you can use the done bit to seal in whatever enabled the TON so it stays enabled and stays done, so to speak. Next thing we're going to do is we're going to use a TON instruction to mimic a TOF instruction. In other words, if you're after a delay off, you want a bit to come on and stay on until some delay time after an event left. That's what we're going to do. The first thing I did is I had you save this current project, and then next we're going to edit the logic. Well, we're slowly working our way to this point in the lab, which is page 196 and 197 or so in your lab project manual, and that is using a TON to mimic a TOF instruction. In other words, how to use an on-delay timer to mimic the behavior that you, or the function of bits that you get from a off-delay timer. And I had you edit your logic so you had a TOF and a TON so we can accurately compare them. So if we can get these two bits right here, basically the timer timing and the done bit, and their influence on these outputs. So if we can get these two outputs down here, output 2 and 3, to behave the same as 0 and 1, then we have the TON instruction and how we're handling it, how we programmed it to behave the same as a TOF. We get the benefit of a off delay, but we don't use the TOF. However, before I get there, I had gone to View, Toolbars, and I had restored the factory toolbar layout. And it moved everything back where it was. However, we do want to get the maximum vertical space for our logic. Some of these toolbars, we can move them to a different location. See how it goes vertical there? Now it's over here. By all means, play with your display. Now this one right here, I'm going to drag it out of there and I'm going to close it because I don't need documentation languages. This one, we do need that. We occasionally need to go up and get an instruction, and so we can drag it off to the side here, and we can drag this over a little bit. We don't need that much horizontal space. And this path right here, we really don't need that, so I'm going to drag that down here, then hit the X to get rid of it. This is not a bad idea to keep it, but we can move it over here so it's out of our hair. And see, there's the Finalize All Edits button, Start Pinning Rung Edits. This is your menu for picking instructions. And then of course the online toolbar, we can drag that out of there. I don't like the way it looks on the screen here. You can't really tell where it's at. I guess that's close enough. So now you see we have a lot of vertical space here. This toolbar right here you can't move. Okay, the main toolbar or the title bar. So this is as much vertical space as you can get. And you will get used to seeing these over here. And by the way, if you click behind them, they don't disappear behind the controller organizer. And you can close the controller organizer as well if you need more horizontal space. And really, there's nothing over here that we access that often other than double clicking on program tags or controller tags as we're doing these labs. I'm going to move this over just a little bit. Too much. Here we go. I had you save your project as beginner, your processor number, TON, TOF. Edit the logic as you see right in front of you. Go online with it in the run mode. All inputs off. I look over at my digital field device simulator. All inputs are off. And I'm in the remote run mode, you can see right here. And I made a point in the manual of making sure you understood that it's the comparison of output 0 to output 2 and output 1 to output 3 that we're mainly concerned with. In other words, we're controlling these bits as the result of this logic, and we're controlling these 2 bits as the result of this logic. And both of these groups of rungs, these 3 rungs and these 3 rungs, are controlled by the state of input 0. Now the first thing you probably noticed is that here we have inverted. So this was a delay off, meaning that we turn this bit on and really nothing happened other than the enable bit come on, the done bit came on. But when we turn it off, that's when things happen. This rung is true when you turn it off. So that's the first change we made. The other change we made was with the done bit. You see with the TOF, when you enable it, it's done. But it's really not done because it hasn't started timing yet. And then when it's done timing, it's not done, even though it just timed out. So we've inverted the action of the done bit. We've flipped it over, so we have the invert to control output 3. So those are the 2 changes that we made. We're looking at the opposite state of permissives or conditions that we were with the TOF, and we've inverted the done bit so it is the inverse of what the done bit would have been if we were just doing a TON. Is the state of outputs 0 and 1 identical to the state of outputs 2 and 3? Well, off, 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 off. So the answer is yes. While observing the outputs of both sets of rungs, switch input 0 to the on state. You see the bottom bit goes on, output 1, output 3. However, if you look at the instructions, you see enable and done is set, enable and done is not set, because this rung is no longer true. But this rung is true. But remember, this is a TOF. But our goal is to get these 2 bits to behave exactly the same as these 2 bits. Therefore, if these two bits reflect the result of a off delay timer, and these two bits reflect the result of a non-delay timer, but they behave both the same, then we're using a TON, a non-delay timer, to mimic an off delay timer because the end result is the same, even though we've inverted a couple things to get the behavior. Is the state of output 01 identical to the state of output 03? Yes, it is. While observing the outputs of both sets of rungs, switch input 0 to the off state. Now this is where the rubber meets the road, because we're after an off delay, but with a non-delay timer. So watch the bits. I'm going to switch it off. See, both bits are on now. And they'll be on until the timers time out, and then both bits are off. So you see we got the identical behavior. Is the state of output 01 identical to the states of output 03? Yes. Were both timer instructions accumulating? Yes, they were. When the timer instruction accum equals the presets, that's what you're looking at right now. Now notice that even the accum is still at 5,000. In other words, with the off delay, this doesn't get cleared until this goes true. When this goes true, then it clears the accumulate value. In the case of the TON, because we inverted the input, it's still, the rung's still true, so the accum value is still there. Now the only difference between these three rungs and these three rungs is with the rung being false, rung 0 false, you don't have an enable and a done bit. But these two bits are both off. With the TON, because the rung is true, it's timed out, enable and done bit is there. But because we've inverted the done bit, this output is off. All that we care about is that the final result, output 01 and output 23, is identical between these two. You may want to tuck this away in your toolkit for an off delay. Use an on delay timer, invert the permissives, the conditions that make the rung go true, and then invert the done bit and you're all set. Try this sequence of operations several repetitions until you can clearly follow and understand why the outputs and not the timer timing and done bits behave identically. We don't care about the timer timing bit and done bit. We only care about the end result, because the timer timing bit and the done bit, they are not the goal. The goal is to control devices. As far as the states of the four outputs in relationship to the state of the input 0 and the timer preset, is there any difference at all? You could say yes and no, because we have inverted the input 0. But in the current state of input 0, off here and off here, they're identical. The difference is we have a true if off instruction instead of a true if on. But the input 0 is off in both cases, and these two bits are off and these two bits are off. Looking at the state of input 0, not the state of these instructions, but the state of input 0 versus state of the outputs, they are identical. If you want to use a TON to delay an off state after an event, input 0 switching to the off state, which conditions do you invert in the logic? Well, we've mentioned that several times now. You want to invert the rung condition for the timer instruction and invert the instruction that reads the done bit to control your final device.